Today I'm going to walk you through why probabilistic risk analysis, otherwise known as PRA, is not just an advanced budgeting technique, but a necessary governance mechanism for modern municipal IT. Across all literature reviewed, there's a consistent warning that flat funding cuts increase fragility, they weaken critical nodes, and they significantly increase the probability of cascading failures. Municipal IT is now a complex, interdependent system of systems. That complexity makes deterministic budgeting obsolete. What I'll show today is how PRA aligns with theory, risk science, and operational reality, and why our budgeting process must evolve accordingly. Here's the roadmap for today's discussion. We begin with the theoretical foundations of complex systems, soft systems, and systems of systems engineering. Then we'll move into PRA, organizational resilience, and financial contagion theory to build the conceptual model. From there, we examine deterministic budgeting, compare it to PRA-based allocation, and discuss governance, political economy, and ethical considerations. Finally, I'll close with practical next steps for implementation. Complex systems theory tells us that failures propagate. Underfund a critical node like identity management or core networking, and you don't get a small contained outage. You get a cascade across dependent services. Flat across the board cuts ignore these dynamics and actually heighten system level fragility. The literature converges on this. Deterministic cuts are misaligned with how modern IT systems behave. Protecting critical nodes is not a luxury, it's the foundation for resiliency. Our analytical toolkit integrates PRA, system of systems risk modeling, multi-attribute utility analysis, and complex systems diagnostics. These methods allow us to quantify uncertainty, identify asymmetric risk contributions, and allocate resources based on marginal risk reduction. This is the methodical backbone of creating budget decisions that are mathematically reproducible, empirically defensible, and operationally sound. This methodology is built on a couple of assumptions about system boundaries, data quality, risk propagation, and validity of expert judgment. By making these assumptions transparent, we eliminate hidden biases that plague deterministic budget decisions. The point is not to claim perfect prediction, but to be able to establish credible, evidence-based approximations of risk. So some limitations. No model captures reality perfectly. The limitations here include uncertainties in probability estimates, incomplete data sets, and structural simplifications in the modeling process. Acknowledging scope limitations is essential because deterministic budgets hide their limitations while PRA exposes them. Some human factors that are present during this examination. Human factors present a major risk, including cognitive biases, inconsistent judgment, and institutional inertia that can degrade the effectiveness of PRA. If staff undermine or misinterpret the model, results degrade. That's why training, transparency, and governance oversight are essential. This flow illustrates how PRA integrates into the existing budgeting process. We gather data, build the model, generate utility-weighted outcomes, and then run optimization under constraints. The output is a risk-informed budget allocation that fits within our fiscal boundaries. Complex systems theory predicts cascading failures where critical nodes are underfunded. Soft systems methodology reinforces that public IT systems are irreducible and constantly evolving. Deterministic budgeting assumes the opposite, that systems are simple, static, and independent. This mismatch is why flat cuts consistently produce unintended failures. Systems of systems engineering shows that some subsystems carry far more risk than others. Decision theory reinforces that rational decision making under uncertainty requires probabilities, consequences, and preferences. Flat budgeting ignores all three, making it a poor decision-making tool. PRA aligns with both engineering and decision theory. PRA provides inputs for utility-based optimization, meaning that we can mathematically tie spending to risk reduction. Organizational resilience relies on monitoring, analytics, redundancy, and adaptability. Funding cuts erode exactly those capabilities. PRA helps prioritize investments that strengthen resiliency instead of inadvertently dismantling it. Financial contagion theory teaches us that risk spreads through interconnected networks. IT behaves the same way. An attack or outage in one system cascades into others. PRA incorporates these interdependencies, and deterministic models do not. That's why PRA is essential for understanding system-wide risk exposure. This slide represents a risk-weighted portfolio view, ranking systems based on their probability of failure, impact, and interdependencies. This visualization helps us target investments where they have the highest marginal risk reduction. Our conceptual framework rests on 4 pillars: complexity theory, system of systems engineering, decision theory, and utility theory. Together, they create a cohesive model in which we can understand how systems fail, how risk propagates, and how decisions must be structured in order to maximize value. Several journal articles were reviewed, and the literature converges clearly. PRA is the only defensible budgeting method under uncertainty. It is already used in aviation, nuclear energy, and high reliability engineering. Local government IT shares those properties: interdependence, consequence asymmetry, and uncertainty. So PRA is the logical governance tool. Deterministic budgeting, which are flat cuts and incremental baselines, is very popular because it's easy and appears fair. But operationally, it's neither. It ignores system impacts, interdependencies, and nonlinear risks. The rationale is simplicity, not effectiveness. In enterprise IT, 2 systems with identical budgets can have radically different risk profiles. Deterministic budgets cuts ignore this. They underfund critical systems and overfund low-impact systems. This misalignment increases risk and wastes money. From our text, Pinto and Garvey argue that deterministic systems thinking cannot model emergent behavior in complex enterprise environments. Municipal IT is exactly such an environment. Their critique supports the need for risk-informed approaches that recognize uncertainty, propagation, and emergent failure modes. Building a municipal risk model begins with defining the system boundaries, constructing a risk register, estimating probabilities, and quantifying multidimensional impacts across financial, operational, legal, safety, and reputational domains. We transform multidimensional impacts into value functions: financial loss, downtime, system impact, regulatory exposure, safety risk, and reputational damage. These are combined in an additive value function. Leadership then assigns weights based on organizational priorities and risk tolerance. With probabilities, impacts, and utility weights defined, we compute risk scores that guide portfolio level decision making. This tells us which systems drive the most risk, how capability level dependencies behave, and where resources produce the largest reduction in portfolio exposure. Using capability portfolio and dependency models, we identify critical nodes where failure cascades into multiple services. These are the systems that cannot absorb cuts without causing exponential risk increases. PRA highlights these, and deterministic budgeting ignores them. The knapsack model maximizes risk reduction under a fixed budget. Each system has options: fully fund, partially fund, defer, or retire. Each choice produces different risk reductions. Optimization tells us which combination yields the highest portfolio value. When we compare flat cuts to PRA-based allocations, the difference is stark. Flat cuts unintentionally underfund high-impact systems. PRA prioritizes systems that drive the most risk reduction. Simulation experiments consistently show that PRA yields safer, more resilient outcomes. Sensitivity analysis lets us explore how risk tolerance, attribute weights, or budget changes alter the optimal allocation. Scenario analysis allows us to model emerging threats like ransomware and see how they reshape priorities. This resilience is impossible with deterministic methods. Subjective probabilities are valid when consistent with probability rules, but model risk remains a challenge. Missing dependencies, outdated data, or poor model structures can degrade accuracy. Governance and oversight mitigate these risks. PRA makes trade-offs explicit, which means some departments will lose funding. That can trigger resistance. There is also a risk of gaming, manipulating estimates to protect budgets. Oversight, transparency, and independent review protect this process. PRA fits directly into the annual budget cycle as a pre-budget assessment. Risk dashboards make complex results understandable for executives, council, and the public. This improves transparency and strengthens confidence in the process. Budgeting isn't just technical, it's ethical. PRA may maximize utility but still burden vulnerable populations if equity is not factored in. Legacy systems can distort allocations. PRA helps expose those inefficiencies and open the door for equity-aware adjustments. PRA aligns with risk management but challenges political norms of equal pain across departments. It's more complex, which can reduce political appeal, but complexity should not be a barrier to safety or resilience. In summary, flat cuts are dangerous. They increase systemic risk and lack analytical rigor. PRA enables smarter prioritization, integrates uncertainty, and optimizes resource allocation. CIOs and budget offices need to use these tools. Oversight bodies benefit from the transparency they bring. My recommendation is to pilot PRA in a single capability, say public safety or communications. Compare outcomes against traditional budgeting, document the results, refine the process, and then expand. PRA is scalable and benefits grow with each iteration. The next few slides are the articles that I reviewed for this presentation.